Queues from scratch. This is starting to become one of my favorite series on this channel, where I'm just building all the data structures that people use on the day-to-day from scratch, and just digging deep into like how these data structures are implemented. So I could just hammer it in, like what are the common functions provided, what are the runtimes, etc. Like I mentioned before in the other videos, if you're not very comfortable with each of these data structures and algorithms listed below, practice implementing from scratch. And that's from Cracking the Coding Interview. And already covered linked lists in a separate video, stacks in a separate video as well. Now we're pretty much getting into queues, but stay tuned in my channel as I just dive deeper into all these data structures and algorithms and concepts and implement all these from scratch. Cool. So let's just go over the basics of what a queue is, and then we'll just get straight into implementing. Pretty much a queue implements a first in, first out ordering. So it's basically like I have another video called queues, everything you need to know, and it's essentially like a line. Like pretend you have a roller coaster. The first person to line up for a roller coaster is the first one to get serviced, right? And then the next person is the next one to get serviced. This is if we put the number of ordering to, this is the third person that gets ordering. If another person comes in, right, this fourth, fifth, there'll be the sixth person, right? So the first person in the line is the first one to get out. Very common in the real world. We're pretty much just going to be implementing these operations right here, which is adding an item to the queue. So it adds an item to the end of the queue. So that's like somebody jumping in the line. And then also remove. It removes an element from the front of the queue. Front of the queue. So when you remove, it removes the next person who's been waiting in line the longest, essentially. The first person to jump in. Peak returns the front of the queue. So if I haven't serviced A yet and I peak, it'll tell me A is the person in the front of the line. Is empty and size are just common ones that you want to implement for a lot of different data structures. So one thing you'll see is like queues are implemented using linked list and not arrays, right? So you don't want to use an array there, and I mentioned that in my other videos because when we're using a queue, we're popping from the front of the queue. So when you pop from the front of an array, now you have to shift all the elements to the right of the first element by one. So that leads to O of n time complexity on like popping from the front of the queue. So using a linked list data structure is more optimal. What else? Cool. Let's just get straight into like implementing this. So we'll start like what I usually do is take a picture of these operations. We'll create a class called queue. Oh, and one thing to note is if you're using Python, don't implement this queue by yourself. Use this collections DQ, which is a double-ended queue, and I'm pretty much going to implement this double-ended queue from scratch. And yeah, use this thing. This is essentially a queue, but we're implementing from scratch because that's what we do. Define the constructor on the class. It's closer. Yeah. Define the constructor on the class. Define the functions. So add. We're adding an item to the queue. Def remove. It's kind of like a DQ. So removes the element from the queue. Self. Peak. Self. Pass. Then we have is empty. Use snake case here for better Python standards. We'll do size. So Cool. Let's just get right into it. Adding an item to the queue. Let's bring this here. So I'm going to implement my queue using a linked list, a doubly linked list more specifically. And like in my other videos, I'm going to use two sentinel nodes. Started off with a head and tail sentinel node. This is what an empty queue looks like. And once we start adding elements, since we have the sentinel nodes, it'll make it a lot easier to sort of add elements. We don't have to handle edge cases that much. So do something like that. So pretty much we're just gonna create this like structure in our constructor with the two sentinel nodes and the head and tail. So let's say like in all the other, like in the stack class, or yeah, in the linked list, we'll create a node. Nodes taking a value in a left and right pointer, or sorry, let's say next and previous. Start these off at none. Then we'll do self.val equals val. Then we'll do self.next equals next. Self.previous equals previous. So we have that, right? So we have our node data structure, and nodes will point to other nodes. So I'll create like a head and tail. Or sorry, I'll create a head and tail. These are the sentinel nodes. Put one at negative infinity. Tail at positive infinity. Then we make self.size equals 0. So we're just initializing the queue. Self.head.next equals self.tail. Make these class level variables or instance variables. Then we'll do self.tail.previous equals self.head. So I don't know what's complaining about. Cannot assign member size for type queue. Oh, just say length. So what we essentially did is we just created this like empty queue, and now we want to add an element. So to add an element, we create a new node, right? Equals node, and then we pass in, like, let's say they're passing in values, so we're gonna pass in a value here. Now this is just linked list operations. We're gonna say head. So we're gonna, since it's a queue, we want to operate from the tail. We want to insert stuff from the tail. So we're gonna say we're gonna take the tail dot previous and make its next value point to here instead of here, right? Yeah. So we're gonna do self.tail.previous.next. Self.tail.previous.next equals the new node, right? And now we make the new node dot previous equals self.tail.previous, because we still have that reference, and we make new node dot next equals to self.tail. So we're essentially creating these specific links. Then finally we take our new node we take our self.tail.previous equals to the new node. So we make this connection and we delete that. Let's see. Cool. Now let's kind of like just even this out a bit. Turn it like this. Turn it like this. because we're gonna add a bunch of elements. Let's say that was A. Do this. So that we added A, and then we're gonna increase the size of our. So now let's just instantiate this queue quick. Let's implement a print function. And to print the queue, we'll pretty much start at the head here, and then slowly iterate through by following the next pointers. So how we do that is we start at current equals self dot head dot next, because I don't want to operate on the head because that's a sentinel node. And I'll be like, while the current is not equal to self dot tail, we're gonna keep going, and I'll have the result here. And I'll say current equals current dot next. That's how you move it for. That's how you follow the next pointer, and then we do result dot append current dot val. Then we like literally print the result here. So let's do our queue dot print. Should print out an empty list. Cool. And then let's do queue dot add like A, queue dot add B. Now finally print again. Now we get A and B. See, now we're adding. You'll see that it's adding to the end of the queue, right? And now when we pop, it should pop from the front of the queue, which is A. So let's implement that function. Let's implement that is empty. Return self dot size equals 0. Length return self dot size. Or let's just do, we don't even need this function. Let's try this. Queue dot, we'll print queue dot is empty. Should return true, but eventually after we add like the first element, that should return false. Cool. So let's implement remove a element. Like we removed a few. So how we're going to remove an element is we want to remove from the front of the queue. So that's why we'll be working with the head again, or head this time instead of the tail. So what we're going to do is we're going to want to take the head and then make this one. So first we want to store like the element we want to return. So let's say remove is like return element equals self dot head dot next. But if they want, like, we need to do bounds check here. If this queue is empty, then we just return. But we want to like throw an error or something too. But right now I'm just gonna print like is empty. Right? So now pretty much what you do is like if it's we grab like the element that we want to return, which is self.head.next, that value, and then what we want to do is we want to say self.head.next equals like we want to take the return element and we want this element to point to who the return element is pointing to. So this, right? Then we want to take self.head or self.head.next.previous. So we're getting the head and we're following the next pointer now, and we're assigning previous equals to self.head. This is just like pointer magic, and you just need to make sure you don't overwrite the pointers, right? So now pretty much we have this. We remove these two. And then now, finally, we take our return element dot next and none this out. doesn't really matter, but I like to do this just for cleanliness. That kind of like nulls this out, and now we could just return this value right here. So let's do print removed return element dot value, and then we just return that return element, right? So now when we remove, we should remove A, and then if we call it a second time, we should remove B, because those are the first people to hop in the line. So remove A and B. Finally, when we print, we're left with C. So I'll analyze runtime complexity after. Make a note of that. Or let's just do it right now because we're already here. So you can see like adding an element to the end of the queue is a O of 1 operation. You could see that's only the case because all I need to do is when I add a queue, just like create a new node and then update a bunch of the different pointers. So that's why that's O of 1. Same thing with removing a queue. You see that when I removed the queue, all I had to do was reassign a bunch of the pointers, and this will always, like, no matter how large the linked list is, this operation is not going to get any longer. That's why we say that's an O of 1 operation. It's constant. It doesn't grow as the input size grows. That's remove. Peak, you're always just looking, all we need to do to implement .peak is literally go like peak. We say self.head.next.value. We could also return that. Say top or front. Give better variable names. Right, and then obviously we do this is empty check as well because you don't want to peek in a queue that's empty. You'll get error bounds. So all that's doing is literally looking at the head.next and looking at the value. So that's always a constant time operation as well. And then is empty in size. Yeah, you're just checking these sizes, and you could see like that doesn't grow with the input size as well. So cool. Let's just see queue.peak, what that does. This should return a C. Yeah, peak C. And then when we print, if we peaked, we shouldn't have popped that value. And then let's just remove a couple times. It should work the first time and remove C, and then say is empty. Ooh, look, we hit the remove here. Oh, okay. With the remove, I wasn't decrementing the size. So we get here is empty, right? And then lastly, let's just print. We can see it's empty now. That's how you implement a linked list, or sorry, not a linked list, a queue from scratch. You could see that it's about 60 lines of code, but hopefully it's not too complicated if you watch my linked list video and also my stack from scratch video. Let me bring that up here quickly. I'll show you my playlist that I've been working on. So I have this how to get good at lead code playlist. You can see I cover arrays from scratch. That video is doing really well right now. I have linked lists implemented from scratch, dropping in December 4. Then I have stacks implemented from scratch December 8. And I'll be dropping this video probably like December 12, I think. So yeah, this video is going to be queues implemented from scratch. So watch all those ones if you want to understand how to, like, it'll help you easily implement the queue from scratch. But also, thanks for watching the video. I'll see y'all in the next video.